Hello, my name is Michael Ulrey, and I'm here today to talk about Bell's theorem in general and the issue of locality in particular. I am a retired engineer, spent most of my time in the aerospace industry. Now I'm retired, I'm interested in using Mathematica to follow my hobby of physics subjects. One of the key things here that I'm interested in is non-locality, the whole thing that concerned Einstein back during the 30s when Einstein, Podolsky, and Rosen wrote their famous paper. And then Bell's theorem in 1964, which was a response to that kind of turned Einstein's argument on its head and said reality must be non-local. Bell's theorem is one of the most important results in the area of quantum theory foundations. It's also one of the most controversial, and that's one of my interests in it. For example, why is there still so much activity, conferences, papers, debates surrounding this paper? I looked up the Google citations, Google Scholar citations for Bell, John Bell. It's not decreasing, it's increasing. And look, 2017, there were over 6,000 papers that cited John Bell one way or another. Now, I'm not saying that was all about the things I'm about to talk about today, but still, that's quite a bit of interest in that very old paper. The Vaxjo conferences, I don't know how you pronounce that. It's a Swedish name, run by Andrei Krennikov, a Russian mathematician who runs these conferences every year. There's still fierce disagreements among the experts. Another thing I would recommend you looking at if you're interested are these, there's a paper and a corresponding YouTube video by Tim Maudlin where he maintains that a lot of mainstream physicists totally misunderstand what Einstein was concerned about and therefore misunderstand what Bell actually did. It's not randomness but in the role of probability in QM, quantum mechanics, but the implications for non-locality that really was Einstein's concern. And very mainstream things like Physics World has a video out there where they completely say the wrong thing about what Einstein was concerned about. So even today, there's concern about this, or controversy about this. Okay, who am I to offer my 2 cents? I'm admittedly a complete novice, not a complete novice. I did take physics in college, but I got my degree in pure mathematics and information theory. Mostly I worked as an engineer at places like NCR, Raytheon, but almost all my career at Boeing as an aerospace engineer. So I was doing very practical things. I wasn't doing quantum theory, but it's always been a hobby of mine. I got to learn Mathematica working on the job, and I love to use it in retirement, 2 years now. And it's just so much fun to use Mathematica to explore ideas, to try out things, to draw pictures, do manipulates and interactive graphics and discover things and then try to prove them. It's a very fun way to approach it. So keep in mind, I'm an amateur. I've got some ideas that help me understand Bell's theorem, maybe to help other people, whether they be amateurs or professionals. But anyway, I'm just telling you the facts here, so you'll know. So what are we trying to do today? 3 things. I'd like to show you a framework that I've kind of developed for my own understanding. It's probability models with parameters. I want to show how these models relate to each other with a heavy emphasis on diagrams and pictures. And I want to shed some light on the very confusing relationship still debated between realism and locality as defined by Bell. So here's just diving into, I'm not going to do the traditional way of starting with the whole history of Bell's theorem. I will do that later, but I just want to give you the punchline here that I'm going to show you 5 models, 3 of them that really mean something physical. Bell local, Bell real, and quantum mechanics. The other 2 I call maximal and minimal are just sort of containing, or say bookends to the other 3. The maximal is like a universal set that includes everything, and the minimal is like everything includes it. It's a singleton. Those are sets of correlations that I have in this partially ordered lattice. So you'll see that Bell local is contained in Bell real, and that's contained in maximal. And those Bell real and Bell local are different than QM. QM is on a different path. There are intersections between these two, but neither one contains the other, hence it's not below or above QM quantum mechanics in this diagram. And I'll be explaining a little more about what all this means as we go along, but I just wanted to show you the main points of this. So a probability model is Bell real if all of the so-called CHSH inequalities hold. That stands for Clauser, Horn, Shimoni, and Holt, who wrote a paper in 1969 which generalized Bell's inequalities. That's what I'm going to talk about in this. So whenever I say CHSH, just think Bell generalized. If a probability model is Bell local, then all the inequalities hold. However, if all the 8 inequalities hold, it's not necessarily Bell local. Now Bell real are that's an if and only if. Bell local, it's not if and only if. The local models are a proper subset of the real models. And as I said, the QM and Bell real models don't have intersections, but neither one contains the other. Now, let me just again make a disclaimer. None of this is, well, some of it is not new. I think the viewpoint is new, but the result that I just said is not new. Number one is not new. That's just Bell's theorem together with Fine's theorem, which he proved in 1982. There's Arthur Fine. And more generally, it's very interesting that there's been a recent rediscovery, as there often is in mathematics and physics, of some really good work that a Russian mathematician did before Bell in 1962 in a Russian journal, A Theory of Probability, which was published in English by Siam in their Theory of Probability translation. Vorobev, any Russian speakers in here? I'm probably massacring the name. Vorobev, whatever it is, did a very general paper on consistent families of measures, which subsume all this stuff about Bell's inequality. But I don't think the quantum physicists ever knew about that. And it isn't until recently you start to see papers saying, well, why didn't you look at this guy before? Well, he did pure mathematics, and the physics world probably didn't pay attention to that. So anyway, here's some pictures. I want to get to the punchline first. You won't know exactly what all this means yet, and I will explain it subsequently. But I just want to show you in pictures kind of what I discovered by trying to understand this on my own. The first row is a set of correlations. What I'm going to be talking about throughout this talk are correlations. If you know the famous experiment, the EPR experiment, the aspect experiment, you have Alice and Bob, who are separated by a great distance. An entangled system sends one particle to Bob and one particle to Alice, and they do some measurements. And there's some correlations that show up. Alice has 2 angles to set her measuring equipment at. Bob has 2 angles to set his equipment at. Together that makes 4. So there's 4 possible correlations they can measure. So what you're looking at is spaces of correlations, which I'm going to denote W, X, Y, and Z. But human beings don't think in 4D, so I have to do slices through the 4D space. So each of these 5 things in each row is a slice through the correlation space of that model with the W, the first correlation, set to either -1, -0.5, 0, 1/2, or 1. So on the ends, the left end is complete anti-correlation in the W coordinate. On the right is complete correlation, W equals 1. And in the middle is no correlation in the W coordinate, 0. Now the first row is what the quantum theory predicts for the correlations. Now look at that. And then look at the Bell real row. Now what Bell was trying to do was say, suppose I assume reality or locality, can I reproduce what quantum theory looks like? Now there's a whole bunch of emphasis in the literature on one number. They look at 2 and 2 times the square root of 2, or 2 numbers, 2 and 2 times the square root of 2. Bell says you can't go higher than 2 for a certain function of the correlations. Quantum theory says, oh yes I can go all the way to 2 times the square root of 2. And they focus on this all the time, and I think, wait a second, you guys got to have a model that replicates that first row with all those fancy swoopy pictures there. And the next two don't look like that at all. And then to go on, I can put them together, and you can see in the first that the Bell local models sit inside the quantum theory, the QM models on the two ends. In the middle, they kind of mixed up. They're inside and outside both. In the middle, you see the same thing with the Bell real models, inside and outside. There's some that are QM, some that are not QM, that are Bell real. And in the third row, the very interesting relationship between Bell local and Bell real is the Bell local models, the green, I call them Pringles. They're like Pringle potato chips. They're hyperbolic paraboloids. And they sit inside, completely inside the Bell real. That's why Bell local sits below Bell real in the partially ordered lattice. Okay, and then here's a picture of the W equals 0 case. The red lines are intersections between the quantum mechanics predictions for the correlations and the Bell local for the W equals 0 case. So there is a way to win the Bell game, if you know what the Bell game is, for those values on the red lines. Okay, you'll learn, I'll talk a little more about this as I go along. So here's the history. Spooky action at distance bothered Einstein. He and his two postdocs wrote a paper in 1935. They say if you take quantum mechanics and locality, there must be hidden variables. In other words, quantum mechanics is incomplete. Bell reanalyzed the whole argument in 1964. He turned it around and said, well, if I assume hidden variables, that is reality and locality, I get a prediction which is inconsistent with quantum mechanics. He derived an inequality that was violated by quantum mechanics. Then that set the stage for a real lab experiment, which Aspect did in 1982, and people have continued to do through the years. And just in the last 2 years, I think it was in 2015, 3 years ago, they supposedly closed all the so-called loopholes in Bell's experiment, in the Aspect experiment. So now it's supposedly proved that Bell was right, that indeed if you assume reality and locality, you do not get quantum mechanics, so you've got to drop one of the three. You either don't believe in quantum mechanics, or you don't believe in reality, or you don't believe in locality. And locality means, non-locality means, like Einstein says, spooky action at a distance. There are influences which can travel faster than light. That's what you have to accept, one of the things you might have to accept, depending on how you choose. Okay, so that's what bothered Einstein. He did say it seems hard, God plays dice, but he also said uses telepathic methods. And Tim Maudlin maintains, if you watch that YouTube video, that it was really the telepathic part that bothered Einstein. He wasn't so concerned about indeterminism. He was more concerned about spooky action at a distance. So I recommend you watch that video. It's very interesting. Maudlin's a very exciting speaker and a lot of fun to watch, and he stirs up a lot of trouble. So anyway, it's a good place to start. What's the experiment all about? You have a source, which is an entangled system of two particles, one sent to Alice, one sent to Bob. They have two measuring orientations each, so a total of 4 orientations. So they have, Alice has angle A and angle A prime, Bob has angle B and angle B prime. They get outputs plus or minus 1. It goes into a coincidence monitor, which multiplies their 1 and minus 1 plus or minus 1s together. If they get plus 1, they're coincident. If they get minus 1, it's anti-coincident. Then they separate all these results into 4 bins depending on the angle settings, and then they compute correlations for all of those. The number of pluses minus the number of minuses over the number of pluses plus the number of minuses, which is always a number between minus 1 and 1. As long as the denominator is not 0, which we'll assume it's not. Okay, so to get those correlations, and then you do some calculations with them, and you compute this S estimate, this number S, where you put a minus sign in front of one of you add all the correlations together, and you put a minus sign in front of one of them, it doesn't matter which one, and at least one of them is going to have, Bell says the S estimate has to be between minus 2 and 2. Quantum theory says no, you can be as big as 2 times the square root of 2 or minus as low as minus 2 times the square root of 2. And those bounds are sharp. You can attain those bounds with quantum theory. And that's the essence of Bell's theorem. If you assume reality and locality, this number that you compute is going to be between minus 2 and 2, but quantum theory says, no, I can go beyond that, okay? So that's the essence of what's going on there. Now, here's a picture of that. This yellow surface is the the quantum surface. This is a different one that I showed before. It's as a function of the angles, which are over here, 22.5 degrees between quantum. By the way, quantum theory says the results they get only depends on the difference between their angle settings. So it's not the angles A, B, A prime, and B prime that matter. It's the differences, the 22.5, 22.5, 22.5, and 67.5, which is the sum of the other three. This point up here, this purple dot at the very top, is the maximum quantum mechanic deviation from the Bell surface, which is at 2. That's as high as it can get. The green plane is at the level 2. That's the highest a Bell real local model can get, whereas quantum mechanics predicts I can go up here to this purple dot. So that's another way of seeing Bell's theorem, okay? And here it is in a table. You compute for the Bell model, and for the QM model, you compute the correlations. Then you compute, and these are the possible values. This looks funny here for the Bell model. Just think of the rows, row 1 through row 16, forms a PMF, a probability mass function. They're non-zero real numbers which sum to 1. So you see that all these numbers are between minus 1 and plus 1, and obviously these cosines are between minus 1 and plus 1. So these are correlations. These are the constraints down here. And then you compute these functions, the so-called S functions, which are represented, the functions are represented by this matrix. And you compute those two S functions. And in the Bell case, you can only get between minus 2 and 2. In the quantum mechanics case, you can go as high as 2 times the square root of 2 as low as minus 2 times the square root of 2. Okay, so that's Bell's theorem in a table and in a figure. Now, finally, I'm going to give you what my models are. And this is kind of the new thing. This is my own invention. I mean, there are ways, it's equivalent in a lot of ways to the standard literature, but people don't look at it quite this way. I've modeled each model in exactly the same way as a PMF, that is a probability mass function, on a set of outcomes. Now the outcomes, you'll see the letters at the top here, A, B, under outcomes, A, B, DA, and DB. A is Alice's outcome. She always gets a minus 1 or a plus 1. Bob always gets a minus 1 or a plus 1. D sub A corresponds to Alice's detector setting. She has two settings, minus 1 and plus 1. Usually you denote that A and A prime, but I like to have these four tuples of minus 1s and plus 1s, which makes it more convenient. D sub B is Bob's two angle settings, either the first angle setting minus 1 or the second angle setting plus 1. Obviously, there are 16 possible outcomes. Now, the QM model says this is what QM predicts, that it's going to be the probability, these numbers all add up to 1 in each column, okay? Every column, they all add up to 1. It's a probability mass function. You get cosine squareds, 1/2 cosine squareds, times delta A and delta B. What does that mean? Well, delta A is the probability that Alice makes her first angle choice. Delta A prime is the probability she takes her second angle choice, and the same for Bob. Delta B is first angle choice, delta B prime is second angle choice. So now these are the 5 models. Now, if you have those 5 models, and this just explains that, you can read this later when you look it up on the website, you will get these correlations. And you'll notice, and again, the correlations are denoted W, X, Y, and Z. For the maximal model, you get these funny looking things. You get the cosine of 2 thetas for the QM model. You get the row combinations for the Bell real and these funny things for the Bell local, and the minimal is all zeros. Now the Bell real, you can easily see that those are between minus 1 and 1, and these are between QM between minus 1 and 1. It's a little harder to see that the Bell locals are, but if you do a little bit of math, you can see that these are also between minus 1 and 1. And then, finally, you do the S functions. And when you do the S functions, you get these values for S1, S2, S3, and S4. It's the same expression with the minus sign in a different place. And each row, each column, you just change where the minus sign is on the terms. So you have the first one, you have minus cosine theta 1, and the second one, you have minus cosine theta 2, the others being plus, and then you have minus cosine theta 3, and so on. But anyway, you get the same result. For QM, you get between minus 2 and square root 2. For Bell local or Bell real, it's minus 2 and 2. And then you can prove that these things are as they are. I just have proofs down here. I'm not going to do any of the proofs. They're all, some are harder, some are easier, but anyway, you can read those on your own later. So I guess I'm almost done. But I can do some other things here at the end if we want to. But let me just summarize what I've done, what I would like to do, and the questions remaining. So I think I showed how to reframe the concepts of Bell real and Bell local in terms of probability models with parameters. And I think it helps me understand what's going on. And I think I discovered a new thing that people don't talk about, even though it may be obvious to some physicists who just don't say it, that, you know, they talk about Bell's theorem assuming locality and reality. Well, I would say locality is a stronger condition than reality. If you have locality, you have reality, but you can have reality without having locality, according to those models and the pictures I showed you. So it's a little bit more nuanced and interesting than it's usually described in the standard literature. This doesn't change what Bell proved, because if you assume a model is local, then you get Bell's inequality, and then quantum theory violates that inequality. So you still have to come to the conclusion that if I assume locality, I can't have quantum theory. So we have to accept, if you want quantum theory, you're going to have to accept non-locality. There's instantaneous action at a distance. So I haven't revolutionized the world. All I've done is have a little more pictorial and organized way to think about it, is what I think I've done here. And I've illustrated that in pictures, and well, I guess I said this other part already. So future work, what I'd like to do is refine these categories, because there are other categories that they talk about in the literature, so-called remote context independence, remote outcome independence, put those into the pictures. And I'd like to classify all the intersections. I showed you some intersections with those straight lines between QM and Bell local, which is kind of interesting. I'd like to do that for all the models. Where can you play the Bell game? And then I'd like to do a closer examination of all the literature, because there's so many terms. There's indeterminism, there's reality, counterfactual definiteness, hidden variables. Do all those mean the same things? Sometimes they're used interchangeably. Sometimes they're used in different ways. It's very hard to tell what people are talking about. So one of my jobs is going to be to try to understand all those definitions other people have and put it in terms of the models I've developed here, so they can be all one place. So, and then there's some questions to just leave you with. Is Bell locality the same thing as Einstein locality? Now, Bell had a mathematical definition, and I've showed you my definition here, which reflects his definition. By the way, if you look at this later on the web, on the Wolfram website, you'll be able to go down and see why I called it Bell local and why I called it Bell real. I have good reasons for doing that. I derived it from the standard definitions, it's just I turned it into a different format. Is that the same as Einstein locality? Einstein was interested in things traveling faster than light, but what things? I mean, this correlation thing, is that the same thing as information traveling that fast? Well, no, it isn't. As a matter of fact, there's a theorem in quantum theory. It's called the no communication theorem, which says you can't transmit information faster than the speed of light, at least using this kind of an experiment, the Bell experiment. So does that mean the same thing? I don't know. I still question it. And then the big question is, underlying Is there, the last question, the big question to me and the thing that I like to look into, and there's a lot of work going on in this area now, is there an underlying deeper pre-quantum theory which simultaneously recovers all the QM predictions that they just emerged, the Born rule and all that stuff just emerges, and is either local or it explains how non-locality works. What is non-locality? How do we instantaneously know about something somewhere else? How does that work? Anyway, that's what I'd really like to answer, but I just went a little small way today. Anyway, thank you very much.